Okay, so good morning, ladies and gentlemen, and welcome back. This morning, we still continue with the concepts of network design. We are still looking at logical network design. Specifically here, we are looking at how to connect to the internet. So network egress design is a subtopic that we are looking at, which is under logical network design. Now, internet access. Internet access is a basic requirement of the enterprise network. So really, you can't design an enterprise network without consideration of how it's going to connect to the internet. So this is one of the basic requirements, and therefore you need to know how to do it and what is required for you to achieve that. Now, several factors that you need to consider is, for example, the type of link that you need to use in order to connect to the internet. So are you going to use a E1, POS, or DSL link? So it depends with availability and cost. Now, one of the most common ways in which we connect to the internet is using either Ethernet or passive optical network links. The other thing you need to consider is the intranet address. Intranet address. Now, generally, we already are aware about the concept of network address translation. And we are aware that in our intranet, we use private IP addresses. But when we go to the public network or the internet, then we use public IP addresses. In the inside, we use private. When we go to the public, we use public IP addresses. So when you talk of internet addresses, then it really means that you need to be aware of the private IP address that you're using, and you need to know how they are going to be translated into the public IP addresses in order for you to be able to access the internet. And the last thing that you're supposed to consider when it comes to doing internet connection is the device that you're going to use to connect to the internet. Now, some of the common devices that are used at the network egress might be, for example, routers, or alternatively, you can use a firewall. Now, this totally depends on the kind of operation that your network actually needs. Now, for example, network address translation, which we have already mentioned that must be done at the network egress, is something that requires a strong processing capability. And therefore, sometimes routers like this kind of strong processing capability. And most of the time, at the network egress, then we implement a firewall instead of a router, because a firewall can not only do NATing, but it can also protect against security threats, and it can also be able to do routing, just like a normal router. So most of the time at the network egress, for a small to medium-sized enterprise, we will deploy a firewall at the egress gateway as the connection device. So those are the three things that you're supposed to consider. I hope it is clear. Now, the next thing we are looking at in the next few slides is how then you can implement what we've just discussed about, the device, the type of link, and the NATing, for example. Now, this is one of the ways. Here you can have a single egress. So you have a single egress. The next one we're going to look at, let me just, the next one is the single carrier, but multiple egress. So we're going to also look at that. We're also going to look at multiple carriers, where you're having more than one ISP, and also multiple egress. So those are the three, I think, that we're going to look at. So let's begin here. Let's begin here on the single egress. So as you can see here, we are having a single interface that is connecting us to the internet or to our ISP. And generally, we at the egress here, we've deployed a firewall to do that. Now, one of the requirements we have is the public IP address requirement. So one thing that we need is we will require a public IP address. So the connection address, the address that is connecting us to the internet, which must be a public address that will be assigned to this interface. Most of the time, you connect to your ISP using a public IP address that is a /30. Remember yesterday I mentioned about the /30 and why most of the time we use /30, because it's a point-to-point connection. Now, on the inside, you'll need to configure NATing. So you'll need an address pool, at least one address pool, because these machines are using private addresses. So translation needs to happen. So on IP addressing, those are the 2 points, and that is what you need. On the traffic type, on this single egress network architecture, we might have internal PCs which want to access the external servers. So they want to access the internet really. And that means that we need to perform NATing. Then we might also have internal servers that provide external services. So for example, here we are having a web server. So people on the internet are supposed to be able to access our server. So again, you need to also cater for that. As we learned when we were learning about NATing, most of the time, because you have a single public address and you have many internal users for NATing here, then most of the time we use network address port translation. While for the server, because several people from outside are actually accessing it, it needs to have a constant public IP address. So for that purpose, most of the time we use a static public IP address for the server. And you remember that type of NATing, I think we called it, was it server network port address translation or something. So those are the requirements of this kind of architecture. Now, with this kind of architecture, really, the advantage is that it is simple to implement and the cost is lower. But the disadvantage is that it's not highly reliable. For example, if this link goes down, then your enterprise will not have internet connection. If the ISP goes down, your enterprise is not going to have internet connection. If the firewall goes down, then again, you're not going to have internet connection. So that is the main problem with the single egress network architecture. It lacks redundancy, which is one of the major requirements of any network design. But for small-sized enterprises, these can work. Now, as we learned when we were learning about the point-to-point protocol at HCIA, we mentioned that we can sometimes connect to the ISP using the PPP protocol or PPOE. Now, when we do that, this particular interface can actually request for a public IP address while initiating the PPP connection. So other than it having a public IP address permanently, when we are using PPOE, it can also request an IP address on the fly, or what we call dynamically. Now, that is one of the traffics that we are talking about. Traffic from our internal users to servers on the internet. The other traffic we need to consider is traffic from outside to our public, to our servers that offer services to people on the internet. Now, in order to implement redundancy, sometimes we might need to have a single carrier. That means we're having a single ISP, but we have multiple egress, So what you're having here is this guy is our ISP. So we're having a single ISP, but we are having two connections to different points of our ISP. So we have one connection there and another connection there. So this one improves the earlier design, which we just looked at, because we have redundancy. If this links goes down, then this one is still working. So at least we have link redundancy, but still we don't have device redundancy. You see, if our firewall here goes down, then we don't have internet connection. So that's the main advantage of this, is that we at least have link redundancy. Now, for each of these interfaces, you'll need a public address. So you need two connection addresses and at least one address pool. So you'll have to configure at least one address pool here, NAT address pool, so that the NATing can be performed on either. Now, when traffic is going outside our network, what you're calling outbound, then we can use to identify the path through which the traffic will pass as it goes to the internet. We can either use a dynamic protocol, which will do the calculation dynamically, like OSPF, or we can use a static route. For example, we can use the floating static route. You remember, with the floating static route, what happens is that one link is disabled, so it acts in standby mode, while the other link acts in the active mode. So if one link goes down, then the one that is disabled is actually enabled almost immediately. So on the outbound, that is how you can control traffic, either using a dynamic routing protocol, or you can also use a static. Now, with traffic coming into our intranet, in order to access our servers, for this one, we don't have a choice. We don't have controllability, because we can't determine how the traffic is going to come into our network. That is, if we have traffic from this machine, for example, the ISP might forward it this way so that it comes in through that link. Otherwise, it can also forward it this way so that it comes in through that link. So really, we don't have much control. We don't have much control with the inbound path selection. And that is one of the disadvantages of a single carrier and multi-egress network architecture. So let's look at the next one. Okay, so that is the outbound, and that is the inbound traffic. So it can follow either of those two paths. So let's look at another one that is an improvement again of the previous one. Here, we not only have link redundancy, but we also have ISP redundancy. So we have ISP1 and ISP2. So in case ISP1 has issues, traffic can still be routed through ISP2. So that is one of the main advantages of this kind of implementation. But the disadvantage, as you might already have guessed correctly, it's very expensive. It's very expensive to implement, and if availability really is a very key factor in that particular network that you're designing, then this is the way to go. Now, the connection condition is that you'll have 2 connection addresses, meaning you'll have at least 2 public IP addresses for each of the interface, and you'll also have 2 different pools. So you'll need 2 different pools so that NATing can be done independently for these 2. So outbound path selection, it can be done again either using a dynamic protocol, or you can configure routing policies. You can configure routing policies to do what we call optimal path selection. So depending on really your preferences, one of those can be used. Okay. On the NAT address pool selection, so we have a pool that corresponds to each of the public addresses. So if your IP address, the source IP address matches an IP to that pool, then you're going to be mapped and routed through a particular path. So that is what happens. Okay. Okay, sorry, I didn't mention here we were focusing on the outgoing traffic. So traffic from our internal to the internet, outgoing traffic. So in the next slide, we are focusing on the server traffic, server access traffic, meaning here, those people that want to access our internal server. So again, here you need to do NAT mapping. So the server IP address must be statically mapped to the address of the 2 address pools. So the link through which a user accesses a server depends on the address used for the connection. Otherwise, with outbound path selection, when traffic is leaving this server going back, we can always configure a static route. Now, the last implementation of multi-carrier and multi-egress architecture is what we call the peer-to-peer mode, which is normally used in data centers. So here, unlike in the other scenarios which we've looked at, here all these servers actually have a public IP address. So NATing is not needed and is not performed in any case. That's why they're called peer-to-peer, because it's almost directly connected to the ISP network. So here we don't have NATing. All the servers have an IP addresses, and actually the enterprise network here is considered as an autonomous, is actually an autonomous system, and therefore must have an autonomous number. And for route path selection, we use BGP. So you have to configure BGP to efficiently route traffic into and out of this network from the ISP network. So that is what we call multi-carrier, multi-egress network architecture, peer-to-peer mode. So let's look at an example, same one that we've been looking at since yesterday. So this is a case. So a campus network connects to an education network using a single link. So MMU connects to KenNet, Kenya Education Network, using a single link, and internal servers provide services for the education network. So design a network egress architecture for the campus network. Design a network egress architecture. So what we're asking here really is, which of this is most appropriate? which of these architectures that we've just looked at is most appropriate for this scenario? Which one? Is it single carrier multi-egress? Is it single egress network architecture? So which one? Single carrier, multi-egress? Which one is most appropriate? Anyone who can mention something? From this, what do you get from this? From this first statement, what do you get? Which type of architecture is this? Because that's the answer actually.
Single.
Yes? Yeah, what did you say?
Single.
Exactly. So that's a single. That's a single egress network architecture. So you can use that if availability is not a key concern for this particular network. And number two, you'll now need to use network address port translation in order to map public IP address or to translate between the private and public address and vice versa. So that is it. That is it about the network egress design. We move on and look at high availability design. So how can we ensure that we have high availability in our network? So this is another interesting topic. Now, the purpose of ensuring availability is to ensure that we don't have network downtime, or we shorten network downtime, and therefore we ensure that the service is not regularly interrupted, the network service. Now, in order to do this, there are two parameters that we must understand. One of them is known as MTTF, or mean time to failure, and the other one is known as MTR, mean time to restoration. Some people also call it mean time to repair. Now, availability is a component that is calculated from this formula. And this formula, as you can see, simply includes the mean time to failure and the mean time to repair or restoration. Now, what is mean time to failure? Mean time to failure is actually the amount of time it takes before you encounter a failure in your network. The amount of time it takes before you encounter a failure in your network. So, for example, maybe a day has 24 hours, and maybe it takes about 23 hours for you to experience a failure in your network within a day. So that is what we call the mean time to failure. A day is too short a time to calculate mean time to failure. Most of the time we do it in per year or something. So, for example, how many days? 360 times 24 hours. What do we get? So, for example, if that gives us, for example, 3,000 hours in a year. So, how many hours does it take for you to experience a failure? Maybe 2,900 hours. So that is what we call the mean time to failure. Then mean time to restoration is how many hours do you take? How many hours do you take to repair and get services back to normal? So is it 2 hours? Is it 3 hours per year? Is it 4 hours? So if you take that particular example, then we can have, for example, let's say 2,900, for example, is our mean time to failure. So we can divide then this by 2,900 plus how many hours in a year does it take for us to restore services? Let's say it's 10 hours. So after we do that, we now need to multiply this by 100. So when we multiply this by 100, we are going to get some percentage. Let's say 98.5%, something like that. So yeah, when you use this formula, it simply means that your network will be available in a year 98.5% of the time in a year. So that is what this particular formula is giving us. So I hope you've understood what MTTF is and what NTTR, mean time to restoration, is. Now, in order to ensure high availability of your network, you need to improve MTTF. So if it was 2,900 out of 3,000, then you need to increase it to 9,950. So you need to improve on it. On the other hand, you need to shorten the MTTR. So if you're taking 10 hours in a year to restore your network, can you reduce this to 5 hours? So when you do that, then overall, it improves. It improves that particular percentage. Now, how do you improve MTTF? How do you improve the mean time to failure? So normally we do this through implementing redundancy. You can implement component redundancy. So in a device, we have several components like the fan, like the CPU. So you can have more than one so that if one goes down, the device will still work. You can also implement device redundancy so that instead of implementing a single egress firewall, you can have two so that if one goes down, your network is still up. Then you can also implement link redundancy. I think this is something we have talked about severally. And you can also use what we call service redundancy. So service redundancy is, for example, when you use protocols, certain protocols, to be able to detect network failures and choose other paths. So for example, when you implement protocols at layer 2, such as STP, we know that STP can be able to enable and disable certain paths if other paths go down. OSPF similarly can be able to dynamically do path switchover if a link is experiencing problems. So on service redundancy, you can also improve by implementing protocols such as BFD in order to quickly detect problems and switch over to alternative paths. You can also implement VRRP. We know that VRRP, we used it to so that we can have multiple gateways and we can have a backup gateway. So that is what we call service redundancy. So those are some of the things that you can do in order to improve MTTF and also shorten MTTR. So this is the first one that we're looking at, component and device redundancy. So some of the components that have redundancy in modular switches and routers include the power module, the SUF, the fan module. So if the fan at the top goes down, the fans at the bottom can still sustain this particular device. We also have multiple power supplies, and therefore if one shorts, then the other can still work, for example. So these are some of the things that really we are talking about when we talk of component redundancy. So power module, fan, MPU, SFU. Now, on device redundancy, we have several ways in which you can do it. For example, when we are using fixed switches, you remember fixed switches, we can do stacking. So we didn't do, I'm not sure whether we did stacking at this level, but at HCIE, it is greatly covered. So stacking is simply combining several fixed switches so that they can operate as a single logical switch. Now, the same concept can also be applied on modular switches. And when you apply them on modular switches, we use what we call CSS, or cluster switch system function. Cluster switch system. So CSS enables us again to be able to combine modular switches into a single logical switch. So that is what we call device redundancy. So let's look at link redundancy. Again, with link redundancy, we have several protocols that can help us to perform link redundancy. One of them is called multi-link PPP. When you're connecting remote disparate sites via PPP, you can be able to bundle several lines so that they act as one. Advantages, they increase the bandwidth. They also, with multi-link PPP, they also support data fragmentation and reassembly, and it can also perform load balancing and backup. Some lines can act as backup. So multi-link PPP is for remote sites, while within our network, at the aggregation layer, for example, we can bundle using the Ethernet trunk, technology, which is a concept we learned at HCIA and also at HCIP. And the advantages again are there. One of the other technologies that Huawei provides is what we call eTrunk, which is able to bundle Ethernet links across devices. So you see, here we are bundling this link between two devices, but how then can you be able to bundle across multiple devices so that these four links can act as one, even though they are connecting different devices? So can you be able to bundle this together? Then you bundle these lines together. So there's a technology called eTrunk, which I encourage you to look at so that you can be able to understand how it works. So it's also one of the link redundancy strategies. So the project case, I volunteer to read for us the project case here.
Project case. After the assessment of both parties, the engineering personnel and the school campus network project group reach a consensus that requirements for network reliability are different on different components. For example, in-access in dormitories requires low reliability, while high reliability is required at the aggregation and core layers.
Yes.
Design a network as required.
Okay, thank you. So at the dormitories, we require low reliability, while at the aggregation and core layers, we need high reliability. So the dormitories, which layer is this? Which layer is this? When you talk of at the dormitories, which layer is this? Yeah? Okay. So at the dormitories, we're talking of the access layer. So we have here is what we have at the dormitory. So we have these switches that are connecting the students directly to the students. Of course, this is the core layer. Just a moment. Okay, sorry about that. So we have a single egress, as we already mentioned. So at the core layer, we simply have a single device. At the aggregation layer, for example, we have two switches. At the access layer, we have all these other switches. So what we are asking here is, at the dormitories, since it requires low reliability, do we need to implement redundancy? At the access layer, do we need to implement redundancy, either device redundancy or component redundancy or link redundancy? The answer is no. So we really do not require, because they have said low reliability. We really don't require to implement any kind of redundancy at that area. But for aggregation and the core layer, we need to implement redundancy. We need to implement redundancy. It can be link redundancy. So for example, each switch is connected via two links. It can be component redundancy, so that these particular switches at the aggregation layer actually have support component redundancy, and also at the core layer. So that is it about this. The other thing you might need to do is, at the aggregation layer here, you configure dynamic routing protocols. So here, because they can do active link switchovers. So here you can configure, for example, OSPF. You can also, to improve the detection speed of OSPF, if you want, you can configure, for example, BFD. And there's also another technology called fast reroute, which you can also configure in order to improve availability at the core and aggregation layer. On the other hand, of course, here, you need to configure STP so that if certain paths have issues, then we can use the available paths dynamically. We can detect and use the available paths dynamically. So that is it about this particular part. Any question or comment? Okay, so just a quick one. So this is the same thing that I've just told you about, what I had just drawn there. So here we can use routing protocols to ensure that we have link switchover and provide redundancy by using the dual star. For example, at the access layer, we can configure VRRP so that, remember we said that normally we configure the aggregation layer as the gateway. So we can configure VRRP here so that we can be able to have a backup gateway. So this can be, for example, the active gateway, and then this acts as the backup gateway. Then we can configure STP so that we can have, again, switchover, link switchover. In case one link goes down, then the other one can be enabled, and we can then go through that particular link. Other optional configurations that you can do is, for example, BFD, so that we can rapidly detect faults and therefore switch over to the alternative link. There's also another technology that is called fast reroute. Fast reroute. What fast reroute does is that it pre-calculates a backup route in order to protect the primary route. So if the primary route goes down, we can quickly switch to the active, to the standby link. So with this, we don't have to do we don't have to do like what we were doing in OSPF. We don't have to recalculate the SPF. We don't have to do loading and route update, because we've already pre-calculated all those things, and we've already identified that in case this links goes down, then this is the new route that we can use. So that is what FRR, or fast reroute, enables us to do. So let's move forward. And now we now want to look at other network technologies, for example, network security. Now, allow me to stop here so that I stop recording. Then I begin this from another recorded video. So asanteni sana.